All right, so the next unit is going to be in magnetism. I put here magnetism. And we're going to start with some concepts. And I'm going to do it a little differently, I think, than it is usually done. Simply because I think it makes more sense. At least it makes more sense to me. So here's what we have. Changing electric field. As long as you have a changing electric field, you will end up with a magnetic field. And in fact, if it's a changing electric field, then you will end up with a changing magnetic field. But the point is that if you have an electric field, and if it is changing in some way, then that change implies that there's going to be a magnetic field that shows up. Now, exactly why is that the case? Who knows? But this is an observable. This is something that we can observe, and this is something that we can express in terms of mathematical equations. So this is where we should start. That changing electric field gives rise to changing magnetic field. It is actually also true that a changing magnetic field will give rise to the changing electric field. We won't really need this quite yet, but we will need this at some point. In any event, this is where we start. Now, changing electric field. So consider a couple options. Suppose you have a charge. Here's a positive charge. Could be a proton. It has the electric field, and the electric field would point like this. And this electric field is static, meaning that nothing really happens with it, doesn't change, it just sits there like that. As long as the electric field is steady, it is constant, it doesn't change, no magnetic field is present. But as soon as it changes, it changes in some way, the magnetic field will show up. And so what we could have is, we could have this charge move. So if you have this charge and this charge is, the charge is moving, so let's say it moves in this direction at some speed v, then with it, the electric field flows, and so the electric field is changing through this space in time. And I would imply that what you will have is, you will end up with a magnetic field that is present, and you could detect that. You could detect that magnetic field. B stands for the magnetic field. I should probably indicate that. Let me put here on the bottom that E is the electric field. And B is the magnetic field. Now you're familiar with the electric fields. You're not really familiar with the magnetic fields, but they're kind of like the electric fields, and you certainly have seen and heard of magnets, and magnets have magnetic fields around them. So, if a charge here moves, if it moves with it, the electric field moves, and so you have a changing electric field, therefore there will be a magnetic field that shows up. How exactly does this magnetic field look like? We don't have to worry about it yet, but there will be a magnetic field. You could also have this charge, so I'm going to redraw that charge that sits here, and it has this electric field that points like this. So there's the charge, there's the electric field. You could also have this charge move up and down. And as it moves up and down, so let's indicate the direction of motion here, maybe with a different color. Here's green. So let's say that this thing moves up and down. And in this case, it was moving to the right. So here it just vibrates up and down. As it moves up and down, what that will do is it's going to cause the electric field to also move up and down. And if that's the case, you're going to end up with a magnetic field. Now, exactly how this magnetic field will look like and what properties will it have, that's a separate story. But as long as there's a changing electric field, which there would be if this charge is moving up and down, you would have a magnetic field. If you have a charge here, and this charge sits like this with its electric field, now let's say that this charge moves in a circle. So it starts here and then it just moves in a circle and keeps moving in circular motion. Well, in that case, what you have is an electric field that moves with this charge, and as the electric field moves with the charge, the electric field is changing its location through space and time, and so you will end up with a magnetic field that is present. You could also have this. So any form of movement of a charge is going to cause present is going to generate a magnetic field. And as a matter of fact, that's probably something that is worth pointing out, because we will use it quite often. So all of this here tells you that a moving charge generates magnetic field. And symbol for that is B. Now again, why is it that that's the case? Who knows? But it is something that we can certainly observe. There's another way you could generate magnetic field using charges. Suppose you have a charge here, and then this charge has a certain electric field around itself. But then let's say you, well actually, all right, so let's draw it. So here's the electric field. I'm going to draw it like this. Here's the electric field. But then let's say you add another charge to it. And maybe another charge to it. So now you have 3 charges here. That would imply that the electric field is increasing. Well, if the electric field is increasing, then there is a change of electric field. And if there is a change of electric field, then you're going to end up with a magnetic field that is present. It'll be also changing magnetic field. But anyways, so it's not just the movement of charge that will generate a magnetic field, but it could be really any change of the electric field. So if the electric field is increasing or decreasing, you will also get a magnetic field. So I'm going to put here if electric field is increasing, you get magnetic field. And if electric field is decreasing, you also get a magnetic field. All right, so these are the ways in which you can generate a magnetic field. And this is sort of the beginning. If you grasp this much, then I think you have a good foundation to move forward and understand where how the magnetism and electricity are related. All right, so let's move on with the concepts. We have this. I'm going to put here on the top that the changing electric fields produce magnetic field or changing magnetic fields. So let's go to atoms and the particles that make up the atoms. Let's consider an electron. So here's an electron. An electron has a negative charge. It is a particle that has a negative charge. It has its electric field. So the electric field here points towards this charge. And well, it turns out that electron, it has a spin. Now, the spin of an electron it's a quantum property. So what is it exactly that it is, the spin of an electron? That's difficult to, not just to explain, but it's difficult to actually grasp. But you can think of it, and this isn't quite true, but you can think of it this way. Here's an electron. You can think of its spin as if it was spinning around its own axis. That's not really true. This is not quite what's happening there, because we don't really know what's happening there. But it has this property of having a spin, and then there's the value associated with that spin. It comes out of quantum analysis, which is something that is difficult to grasp. Maybe it's not even actually possible to visualize what's happening there with the electron. In any event, it has this property of a spin. And you can draw from here in a more or less valid way that if that is the case, then it would be reasonable to suppose that an electron also has a magnetic field. So an electron, E, has a magnetic field, D. And it turns out that it actually does. So the electron will have, every electron has a magnetic field. And so if I am to draw an electric field here around the electron, I also should draw a magnetic field around the electron. And I guess I'll do it. I'm just going to do it like this, to indicate that there's also a magnetic field. And then this magnetic field would presumably loop all the way around. We haven't looked at lines of the magnetic field yet, but I'll put it there anyways in the picture. Now let's consider a proton. So proton, well, here's a positive charge for a proton. Here's the electric field of a proton, so there's your electric field. And as it turns out, the electric field, as it turns out, proton also has a spin. It has a spin. Again, it's a quantum spin, so it's not a regular classical spin where you have a ball and the ball just spins around its axis of rotation. That's not quite it, but for the purposes of this class, you can think of it that way. And so you can think of the proton, every proton as if it was spinning around its own axis. That would indicate that perhaps, well, proton would also have the magnetic field. And it turns out that it actually does. Proton also has a magnetic field. So every proton, just like every electron, also has a magnetic field. And I'm going to draw this here. Here's a magnetic field B. And I'll complete these loops. Don't worry about the lines of the magnetic field yet. I'm just putting it in the picture just for the sake of it being there. And then the last thing is a neutron. So here's a neutron. Now neutron has no electric field, but it still has a spin. So it still has a spin. But that doesn't really help you, because even though it has a spin, even if you were to think of a neutron in a classical way where there's a spin, well, there's no electric field that could change here. So this analogy here, this analysis doesn't help you. Still, as it turns out, and this is something you should know, every neutron also has a magnetic field B. Even though it doesn't have electric field, it will actually have a magnetic field. And so now what we have is that all protons, all neutrons, and all electrons have magnetic fields. In other words, they're all little magnets. All protons, neutrons, and electrons, they're all little magnets. But all atoms are made out of protons, neutrons, and electrons. And so you're forced here to say that, therefore, all atoms must have magnetic field as well. And this is true. All atoms have magnetic fields. So what we could do is, well, you could raise an objection. All right, well, all atoms have magnetic fields. All right, fine, but that doesn't seem to make sense, because not all elements in the periodic table have magnetic fields. Further, you could say that if all atoms have magnetic fields, and then, you know, things of your everyday experience are made out of atoms, then you would also say that, you know, things around you have magnetic fields. And you would say, surely that's not true. For example, a piece of wood is not magnetic, or a glass in a window is not magnetic. Well, as it turns out, what happens is, it's true that all of the atoms have magnetic fields, but not all of these atoms have significantly large magnetic fields. So there are some atoms, for example, iron, nickel, and cobalt. Their magnetic fields are significant, so that if you have one of them, let's say here's an atom of one of them, you will actually have a detectable magnetic field around. So you could draw a magnetic field B that it points around an atom of either iron, nickel, or cobalt. But if you consider any other atom, so let's say you consider aluminum, and if you were to draw an atom of aluminum, you draw it here. There would still be some magnetic field there. It's just that magnetic field would be so small that it would be virtually zero or insignificant. It's as if it wasn't there. So all atoms are magnets. They all have magnetic fields. It's just that only a few of them have significantly large magnetic fields. Now this will bring us to the following. So suppose to the magnets, actually. Let's look at magnets briefly, because I think at this point we're ready to look at magnets, and we'll probably end this story with magnets. So now that we have that all atoms are magnets, but not all atoms have significantly strong magnetic fields. What we could say is, well, what about magnets? So let's say you have a chunk of a magnet here, and there's a north and a south pole, and there's a magnetic field, and so on. And then you have a chunk of something else. So what if we say that this is a chunk of iron? Because magnets, regular magnets, will be made out of iron, and so you're going to have these atoms of iron where, let's draw them. They're lined up like this. One row, let's do another row. And then let's say we pick a chunk of aluminum, and we will also have these atoms of aluminum that sit here like this. And then let's maybe do one more right here, but this is going to be another chunk of iron. And I'm going to do something. So every single one of these atoms here, whether it's aluminum, the atoms in this piece of iron, or atoms in this piece of iron, all of these atoms will have magnetic fields. So let's draw them like this with blue. Let's say that the magnetic field of this atom points like this. Here's the magnetic field of this one. Let's say the magnetic field of this one points like this. Let's draw these two like that. Maybe this one like this and this one like this. Let's draw them this way. This one points like this one points like this, and then maybe we'll do this here. So every single atom here has a significant magnetic field. They all point in different directions. And then let's say that here in this chunk of iron, what we have is significant magnetic fields for all of these atoms, but let's say that they all point in one direction. All right, so a bunch of arrows. And then here's the aluminum. All of these atoms here of the aluminum have magnetic fields, but they are just small. So I'm going to draw like a little tiny dot for each one. They might point in the same direction, some of them might point in opposite directions. Let's draw it like this. And there's that. All right, so, well, what do we get out of this picture? Well, looking at the first picture, this magnetic field will combine itself with this magnetic field, and this magnetic field combines itself with this one. All of these magnetic fields will become combined into one that will form a larger magnetic field, and therefore you're going to end up with some magnetic field on the outside. And this magnetic field will loop itself around and come back to the other side, and likewise here. All of these magnetic fields, because they point in the same direction, will combine and align themselves, and they'll loop all the way around, and now we get a significant, not only internal significant magnetic field, but we'll get significant magnetic field on the outside, where you will have a north and you will have a south pole. Now in this case here, all of these atoms, the magnetic fields of these atoms point in different directions, so they won't really add up. You'll have some weird magnetic fields around close to the surface, but you won't really have anything significant on the outside. So I'm going to put here no external magnetic field that is significant. And then when you go to this chunk of aluminum here, well, there's really, the magnetic fields of the individual atoms is so weak, so small, so insignificant that even if they were all add up, even if they were all to point in the same direction, they wouldn't add up to anything big. And so what we get is a picture where we would say this is a magnet. This is not a magnet. And this certainly is not a magnet. Now, could you take this piece here and turn it into a magnet? Well, the answer is yes, so let's consider that. What you could do is you could place this in a strong magnetic field. So perhaps, let me clean this up a little. Let's remove this because we don't really need that here for the moment. Let's take this, get rid of that. Let's take this whole picture. and let's take it, just move it a little lower here. So if you wanted to turn this piece of iron into a magnet, what you would then do is you would, well, you would want to rotate all of these individual magnetic fields so that they are all aligned. And how would you do that? Well, here's one way to do it. You would take a big magnetic field. So let's say you would take some kind of a north pole here, and you take some kind of a south pole here. And then you would make sure that this field here, you would make sure that the field of this this field here is strong enough so that it points in this direction, and it causes all of these individual atoms to rotate, so that this field here no longer points like that, but rather now, perhaps I'll do it in green, but rather now it rotates and it points like this. This one rotates and it points like this. This one rotates and it points like this, and this one points like this. This one points like that. So you want to place these individual atoms in the magnetic field strong enough to actually cause these magnetic moments here to rotate, and then they can add up and form their own magnetic field. Well, you would want to remove the this magnet here, so this is gone, and then you've ended up magnetizing this chunk of iron, and so now it will be a magnet as well. Now it's also a magnet. All right, now how would you take away magnetism from a magnet? So suppose you have this magnet here, how could you mess up its magnetism? Well, you could do it in 3 different ways. Actually, there are probably more than 3 ways, but here's what you could do. You could heat this thing up, and as you heat this up, you would cause the atoms to vibrate, and they would bump into each other, and they would cause themselves to fall out of alignment. And then you wouldn't be able to adapt the magnetic fields of individual atoms anymore. You could also take the this piece of iron and just hit it against some hard surface, causing a vibration to travel through this ion, and that vibration would cause atoms to fall out of their alignment. You could also run electricity through this thing, and if you were to run electricity through this thing, that would cause this thing to heat up, and with heat, you could potentially cause these atoms to fall out of alignment as well. So you could destroy a magnet in that fashion. All right, well, I think this will do for the concepts as an introduction. Often enough when you read the book, you will run into the concept of magnetic domains. So yeah, maybe I should add that for just to clarify. So let me draw this. Here's what we'll do. Suppose you have a chunk of iron that looks like this, and I'm going to draw dots for individual atoms. So we have a bunch of different atoms. This is a metallic structure, so more or less you have some kind of symmetry, some kind of uniformity here. And I'm going to draw the magnetic fields of individual atoms. Let's say that these magnetic fields point, these atoms have magnetic fields that point like that. Let's say that these atoms have magnetic fields that point like this. Let's say that this here points in the following direction. And maybe this points like that. I think at this point you might be beginning to understand what the word magnetic domain means. So maybe I'll do a few more. And let me put on top what I just did, magnetic domains. So the way I explained this to you, the concept of magnetism in magnets is by using individual atoms. But in reality, you will have clusters of atoms whose magnetic fields align. So here's one domain. Here's another domain. Here's another domain. Here's another domain. Oh, look at that. I missed one. This belongs in here. Here's another domain. And then here's the last domain. So you have these domains of atoms whose magnetic fields point in the same direction. You will have clusters of atoms whose magnetic fields are aligned. It's unlikely that you will have every single atom that points in different direction all over the place. There will be some of them will be aligned. As it stands, this is not a magnet. Not a magnet. But if you could place this in the external magnetic field that, say, points in this direction, then you could cause all of these domains to realign themselves, and then if you did that, then you would end up magnetizing this piece of iron. So you could end up with something like this. Where all of these point in the same direction. Right? And if that is the case, if all of these domains point in the same direction, I didn't draw the same number of atoms, but anyways, then they would add up, and that would give you a strong magnetic field on the outside that would loop around somehow. And now you'd have a north and a south pole. Okay, well, here's your introduction to magnetism. Perhaps the most important thing for you to remember would be, let me bring this back to the beginning, would be this. Changing magnetic field produces changing electric field, and actually this is something we're going to need later. Changing electric field produces a changing magnetic field.